In this series of videos I'm attempting to repair an HP9830A desktop calculator. In the previous videos I'd got as far as repairing a lot of faults with the hardware. There's a fault in the power supply. I've replaced in the logic circuits close on now to 100 ICs. I've never seen a piece of equipment with so many failed ICs, and that started giving me some concern based on the nature of the circuits in this machine, that there was something more serious going on. And usually this sort of thing is power supply related, but I'd eliminated problems with the supply. I've very thoroughly investigated that. The reset circuits seem to be working, the power supplies are stable, they come up in the right way. But I'm still seeing a huge number of failed ICs, and one of the things that can cause that in a machine with this sort of architecture is if the code that's trying to run the machine is going off the rails, and it's causing the circuits to all fight each other and misbehave. So I'd got as far as getting it to the point where it would run the microcode unit successfully, and it then started to try and run the main system code. Now the main system code resides in this board. It's a series of mask ROMs, so it's relatively simple in the way it's configured, although there are some oddities in it. Firstly, in the decoding of one of the address lines, there are two pins for one address line, one high, one low. I'm not quite sure why they've done that. But essentially the way it's configured is in blocks of 2 ROMs per address space. What we have are a series of block selection lines that come from the address decoder, and then we have the lower 8 address lines, and the 8 address lines select the memory location within each pair of ROM chips, and then the block selection lines select the particular block. There are some strange things going on even within this, because all the outputs are hooked together in 2 banks, and then they're combined on the output of the output buffers, and then from here they go to the T register, and the T register is responsible for reading the 16 bits together, and then it can feed those 16 bits into the CPU in a serial form. So what I decided to do is investigate what was going on, so I hooked up the logic analyzer to the output of the T register and the output of the M register. The output of the M register is what determines the address that we're trying to read from, and those two should give me the input and output effectively of this ROM card. So I triggered on various addresses and started going through the code. But so I'll show you what I'm finding and then go from there. So I'll move the camera to look at the analyzer and we'll capture some data. So the way I have the analyzer set up at the moment is it's set to trigger at a hex address of 815, which is actually 4015 octal. Bear in mind that the addresses in this code are shown in octal. So what we have here is the left hand number is a line number, we have the octal address of the instruction, and then we have the instruction value itself followed by a description. So we're set to trigger on address 815 hex, and that equates to an octal address of 4025. So we should be triggering on this address. So we'll do that and see if we do actually capture the correct data. So bear in mind the analyzer is going to capture the data coming out of this particular ROM, so it's this one here. Arm the analyzer, power up the HP, and we've captured some data, and the data we have is B4E3. Now, one of the things with this machine is that the data in the ROMs is inverted. There are inverting buffers going into the T register, so the data stored in the ROM is actually the complement of what's actually required for the instruction. So I'll just invert this data. Okay, so if I invert this value, it gives us this value in binary, and converting that back to hex and then to octal gives us a result of 45434. So in other words, once inverted in the T register, this value would be 45434 octal, and that's for address 4025 octal in the code. And if we look at that address, so 4025, we should have a value of 45434, and that's this instruction. And that's correct, that's what we're seeing. However, if I change the trigger address, then we'll see we're getting a value at this address of C400. Now, to start with, we shouldn't have triggered on this address at all because this is in the boot up code, so we shouldn't be going past this unless I reset the machine, and I didn't reset it, it's just still running. And if I keep rearming, you'll see we're carrying on running past the same point. So something's amiss straight away. Now, of course, it could be a hardware fault, but what I'm doing here is investigating the firmware to see if it matches what's in the listing. This listing is what I'm taking from the original patent, and there are a few errors in there that I know about, so I have to try and figure out if the issues are within the machine, within the firmware, or if the listing is just incorrect and the firmware is fine. If I now do the same thing with this value, so we have C400, I'll convert that into octal and see what we get. Okay, so I've done the same thing here. Taken the value we've captured of C400 and inverted it, and we're getting an octal result of 35777, and this is for address 4030 octal. So if we look at that address in the code 4030, we should actually be getting 31405 and not 35777. So that doesn't match, and this is the description of the instruction. Now, of course, it's possible that the errors in the listing here, as I say, I've taken this from the patent. So the next thing we'll do is to interpret the actual instruction and see if it makes sense in the context of what's going on here. And we'll do it for both the value we've captured and the value that's listed here and see which one makes more sense. So I'll turn the analyzer off and move the machine out of the way, and then we'll analyze the data that we've captured. Okay, so if we look at the data that we've captured, we captured two addresses. One was at 4025, which is this address, and the other one was at 4030, that's this address. These are octal values. So if we now look at the two instructions, if we interpret what we've captured and see what instructions they should represent and see if it makes sense. Now, this is the one that we captured that was correct, and if we get the instruction set and interpret this particular code, I've turned it into binary here, it just makes it easier to interpret the instruction. So the first 10 bits are a memory address, and if we convert that into an actual memory address and see what we get, I'll do it in octal because that's the addresses that are shown in the listing. So what we have here is 1434. So if we need to, we can now see what address this instruction is supposed to be jumping to or reading from, depending on what the actual instruction is. Okay, the next bit, if we look at the configuration of the instruction, depends on what the actual instruction is. So we need to look at the instruction code, which are these 4 bits. So in this case, we've got 100 followed by a 1. So if we look for that combination in here, we'll see that we have 1001 is ISZ, which is increment skip if 0. So this is that instruction. the P, that's this digit, if we look at the code for that, determines which particular page we're going to jump to or from, and that's where the address may or may not be used depending on whether it's a direct or indirect address jump. So in this case we've got a 0, so 0 is current page. So in other words, we don't need to jump to a completely different bank of memory, we can stick within the one that we're currently in. So next is the 16th bit. It's a 0, and if we look on the instruction we'll see that's indicated as being direct or indirect addressing. In this case it's 0, so we know it's direct addressing. So in other words, what we have with this instruction is an ISZ instruction that will stick within the same page that we're in, and it will use direct addressing. So if we look at the listing and see if that makes sense, so this is line 4025, and on line 4025 the instruction should be ISZ, and the purpose of this instruction is just to set an initial value for one of the math functions, which is why we shouldn't keep coming back to it over and over again. This is just initialization code. The code starts here effectively. Okay, so what we'll do now is decode the next instruction. So this is the value that we captured, and if we do the same thing, the first 10 bits are again the address, so that is FF, which is a bit alarming in itself. We shouldn't really be looking at an address like that within the code. And then if we decode the instruction again, it's basically in 3 parts. Firstly, again, we're looking at direct addressing. The instruction itself, if we look for that particular instruction, we can see it's a store, and it's a store of either A or B. This bit is going to determine whether it's A or B, and if we look at the code for that, it's R, and if we look up here, A or B, 1 is B. So in other words, the instruction is store B, and again we're using the current page if we need to use the address. Okay, so this should be a store B instruction if this is correct, and if we look at the listing for address 4030, we'll see it's supposed to be a store A. Not only that, but it's store A of this value. This is, if you like, a disassembly of the code. I don't know how accurate this is, but in sort of the grand scheme of things it should make some sense. And if we look up the address for FWUP, which I've done, then FWUP, I'll print off the relevant page, FWUP should be address 01405. So in other words, this address should be 01405, and that's in octal of course, but even if I convert 1405 from octal to hex, we get a value of 305. So this is 10 bits, don't forget. So this makes no sense. It doesn't match what's going on, and also this address is kind of meaningless within the context of what we're doing. So what I'll do now is the same, but for the address that's in the listing, to see if it's any more likely that the value shown in the listing is correct, and the value shown is 31405, which I've already converted into binary. So if we do the same thing, then this address, and again this is an address that we'll either read from or jump to or whatever, depending on what the instruction is. If I convert this into an actual address, so again I'll do it in octal, so what we end up with is 1405. And if you recall, if we look back at the listing for this address, this is a table that stores values, and if we look at this address, we'll see for FWUP, which this instruction is supposed to be updating, we'll see the address is shown as 1405, which as you can see in the listing, tends to make more sense. But if we decode the rest of the instruction to see if it fully matches the listing, then again, if we pull out the middle 4 bits and try to identify what this particular instruction is, then firstly we know we're using direct addressing and we're on the current page, and that just leaves these 3 bits to identify the particular instruction, which should be 011, which again it is, and it is a store instruction as was shown here, and the value after, however, is a 0, not a 1 as it was in the captured data. And if we look at that, that means it's store A. So in other words, we want to store the value in the A accumulator at this address, and does that match what we're trying to do in the code? And as you can see, it's a store A at this address, which exactly matches what's in the listing, but does not match what we captured. Also, the fact we're getting all zeros from this address tends to concern me. It's normally it kind of indicates a failure mode for the device, and also if you bear in mind these are 8-bit ROMs, you'll see that these 2 bits are correct in both addresses. So in other words, the top 2 doesn't look too bad, whereas the bottom one, it should be this and it's giving us this, so that looks like that particular ROM has failed completely, or at least on this this byte. I have done this for several other addresses. There are some that are correct and some that are just totally wrong, and when they're wrong they're completely incorrect. So what I'll do next is just capture the address bus that's going into the ROMs to make sure it's not reading a completely different address for certain values. I find it highly unlikely because of the nature of what I've been seeing, but I'll do that first. But it does look like this could be a major problem in that the ROMs have failed, or at least some of them have failed. And because they're mask ROMs and the code is put into them at the time of manufacture, and also they're impossible to get hold of, there's absolutely no chance I could get hold of any, even if I had a way to program them, and again the cost would be prohibitive. So I think I have to consider, if the address decoding doesn't show anything up, I have to consider this ROM board is dead. There's little value in trying to mess with it or get it working, because I do want to get the machine working, and it's not really a restoration, it's more of a repair. What I will probably end up doing is making a ROM board for this machine. Making the ROM board is extremely easy. The nature of the circuit means that if we ignore all the complexity in the middle of the circuit, this is just really because the ROMs at the time, bear in mind this was designed very late 1960s, very early 1970s, and these were really the kind of first ROMs available. They did progress a lot over the 5 to 10 years after this, but these were low capacity, and also they had sort of fairly odd requirements for power supplies, for signal levels, and the decoding was a bit peculiar as well. So it meant that making a board to use these was quite complex, and you ended up with a circuit like this. But this could essentially be replaced almost with a single ROM, single modern ROM, and that's what I will probably end up doing. That bit's quite straightforward. The difficult bit is getting the code into a form where I can program it into a ROM. There's about 500 pages of code, and I need to convert these values into hex so I can put it into the programmer. That bit's fairly straightforward, but unfortunately I can only find a PDF of the patent. So if anyone out there has a copy of this code, it's for the HP9830A, and it's a system code I'm looking for, not the microcode. This is the actual system ROM. If anyone has a copy of this in a readable form, that is an electronic form where it can be easily read as a text file, then I'd much appreciate if you could let me have a copy of it. Or if anyone's got the code itself, even if it's in the separate binary files for each of the ROMs, again I could combine them. If not, what I'm probably going to have to do is write a piece of software to parse the PDF and extract these values, but I'd rather not do that if I can help it, because it would take a lot of time and effort. So if anyone does have anything that could help, then please let me know. Otherwise I shall probably have to look at building a replacement ROM card.